Okay, now that we have realized a way to define a line using vectors, maybe we can write an equation for a line using vectors. Why not? I mean, if we can say that a line is a particular, associated with a particular vector, why can't we maybe write an equation for a line in terms of vectors? And we don't typically write an equation for a line in terms of vectors. We write it in terms of x and y. But maybe we can do it in terms of vectors. And we are going to do it using the kind of parametric way of doing it. In other words, we're going to have a parameter t. Now, we're not going to have many equations. We're only going to have one equation, so in a way you could say it's simpler, but a little different than the way we're accustomed to thinking about the equation of a line, so it may not be so simple. But we are going to do it in terms of t. It's just going to be one equation, but it's going to have a vector in it. Now, it's not so strange to have a t times a vector. Remember, t is like time, or in other words, it's just a scalar. And it's not so strange to have a scalar times a vector. We've been talking about that for a while already. We talked about that here. We talked about multiplying a vector times a scalar. Well, instead of 2, we'll use t, so that it can be kind of any scalar. But that kind of allows us to kind of talk about, this vector, or 2 times this vector, this one, or 1.5 times this vector, or 1.25 times this vector, and so on. So we get sort of all these vectors, and of course notice that these are all more or less on the same line, or they are on the same line. But so now we want to try to write a kind of parametric equation of a line, but we're going to not use x and y, we're going to use a vector. So what might this look like? So let's go back to this picture and this picture. And so we're going to define a line that is parallel to this vector. So if I wanted to define a line that goes, actually is this vector and all of its extensions, both forward and backward, what could I say? I could say that the line I'm talking about is basically just all multiples of a, both positive multiples and negative multiples. So that's exactly what we're going to do. So if it was just this line right here, it would be just TA. So we'd just be talking about a set of many, many vectors that are just multiples of A. So first of all, before we get confused, remember that if we're writing in the book, they can type a bold A, but I can't type a bold A. So the other way to write a vector is with an A with a symbol on top. So that just means the vector A, which is bold A. And this means a vector R. And what we want is the set of all vectors R, which are t times A, where t can be any real number. So in other words, we're just talking about the set of all vectors, and we're calling them R, and they're multiples of A. I can't call them A because A is a fixed vector. It has a certain length. So it can't be just A. It's t times A, and that represents, and we're calling those, all of those possibilities, we're calling them R. So it's like this. The set of all vectors R, and these vectors are a function of t, because it depends what scalar we're multiplying, t times A. So there, we did it. We have a vector equation that it's a function of, we could say it's a function of t, but we could also say it's a function of A. And it's a set of many, many vectors, or kind of an infinite set of vectors. So this is basically what we want to do. Now we're going to make it one step more complicated because we don't want just vectors that are, all the vectors we're talking about now pass through the origin, but we don't want, or sorry, yeah, all the vectors or the lines that we could represent so far pass through the origin, but we don't want to be stuck just passing with lines that pass through the origin. So we want to be able, for example, to talk about this line, and what would this be? That would be all multiples of this vector, but this vector we say is translated up. In other words, we add a displacement vector basically to bring it up to here. And then once we've done that with A, then we can talk about all the extensions of A. So we have to add in kind of like a constant here. Actually, it's a constant vector. So the final equation looks like this. So it was T of A, R of T equals T of A, but we add in, we allow ourselves to have a constant, but it's not just a regular constant like we have, like y equals mx plus b, but this constant b is a vector so that we can translate the A that we had running in this direction up to here. So what is the vector b, the constant vector? Where is that in this picture? Well, you can see it. It's right here, b. And what is it? It's from here to p sub 0. So it's that vector. So what we do is we take this vector plus a, plus ta. So when we add a to this, what do? We put it at the tip of b, and we add. And we can add any multiple of it. So we get b, and then multiples of a starting from here. And that's exactly what we want. So the equation becomes R of t, that means the set of all these possible vectors, that's what R stands for, the set of all these possible vectors, and it equals, we say, we allow for a translation up to here, a shift of by b, by this amount here, and then extend in this direction as much as we want. Now b can be 0, then it's going to be through the origin, but we're not insisting that it be through the origin anymore, because we allow for this. Remember, all I had was just the TA. But we have the TA, but we're allowing for b some constant, but it's not constant like a number. It's a vector constant, so it allows us to shift up. And then notice you can't add a constant to this. This is a vector, this part. We don't have anything like adding constants to vectors. We have adding vectors to vectors. We have multiplying a vector by a constant. We never talked about, and we don't talk about, adding a number to a constant. So b can't be a number, but it can be a vector, and that's what we're doing here. We're adding a vector to another vector. We're adding, we can say it either way. We're starting with b and adding this, or we're taking a and adding b to it. So we're allowing this to shift up to this line. So like I said, maybe since we can identify a line in terms of a vector, maybe we can write an equation for a line in terms of a vector, and that's exactly what we did here. This is what we wanted to do. And what do they call this? The vector parametric equation. So it is parametric in the sense that it does have the t in it. For the line, what line? The line through a given point. We want this point, so that's going to give us this vector to get to that point, b. The line through the point p, which p is in, this is all taking place in 3 space, so we need a triple. So this is the triple, whose position vector is OP, so this is the vector that represents p sub 0. And we can, remember, we can write b like b1i plus b2. Remember, we said we can take something written like this And by the way, this is a little confusing notation here because there's no space between P0 and this stuff. It looks like maybe P0 is a function of this, or anyway, but this is basically, we're just talking about the point P0, which has these coordinates, okay? And then we said that we can think of this as in terms of the I, J, and K, like this. We should be able to shift from here to here, hopefully without too much trouble in our minds. And so that's B. And so let me read it again. The vector parametric equation for the line through the point P, what point P? P0, B1, comma B2, comma B3, so it has to have some coordinates, so we're just saying that those are the coordinates, whose position vector is OP is B, and can be written this way as well, and parallel to A. Remember, we want it to be parallel to A, is this. Okay, so this is kind of like a shift, right? We're not really used to thinking about lines as vector equations, or equations of lines as vector equations. In fact, we're barely used to talking about vectors at all, and vector equations are basically, I don't think we talked about vector equations up until right now. So this is all kind of quite new, but it seems to make some kind of sense, right? We have the set of all possible vectors that fall on this line. So we can say that's kind of a vector equation for this line. That's what we wanted to do. Okay, now let's read this. So they say, now we see how to provide equations for lines. First, convince yourself that a line in R2 or R3 is uniquely determined by two pieces of geometric information. One, a vector whose direction is parallel to that of the line, and two, any particular point lying on the line. Okay. See figure 1.2.3, which is here. In figure 1.24, we seek the vector R equals OP. So we're going to remember that we want this line, which basically means we can say either we want all the vectors that extend from here in either direction, or we can say that we want every point on the line. But remember that we have an association between points and vectors. For example, this point here, P, would have 3 coordinates, right? Because we're in R3, we have the X, Y, and Z coordinates here. But we also said earlier that we should be able to sort of interchange between that view, which is of a point and its coordinates, and of the associated vector. So we should just be able to shift interchangeably between these two perspectives. So, like I said, we can talk about basically all the vectors that extend from here in this direction and this direction, or we can talk about the points on the line. But remember that with each point, we can also shift to the vector view of that point. In that case, that would be this vector, from O to P. Now, we're considering this point P to be arbitrary, an arbitrary point on the line. So it could be this point, could be up here, could be down here, could be down here. So we're just talking about an arbitrary point P on the line. So we have a vector from O to that arbitrary point, and we want to identify which points or which vectors provide a point on the line versus all the other vectors that provide points somewhere else but not on the line. So what they say here is, in figure 1.24, that's this figure here, we seek the vector OP, they're calling it R, between the origin and an arbitrary point P on our line L. And then you're saying that's the position vector of this point. In other words, it's the vector associated with this point P. And now, what can we say about this vector? We could say, remember, we're given a vector A that we want to be parallel to our line, and in this case they're drawing it up here, but we have drawn it over here. But in any case, we can shift, we're allowed to shift the vectors around. We could have had it here, but they're drawing it here, make it maybe more clear. So we want the line which is parallel to A, and furthermore we have to say that's not enough, right? We have to say that it goes through a particular point, and we're saying that it goes through the point P0. So now what can we say about this OP? Well, if you look at it, we can see that if you take the vector OP0, remember P0 is given, so we can certainly talk about the vector OP0, that's what they call it, OP0 here, which is they call it B, this vector here. So what can we say about this one here? It's the sum of this one plus TA. In other words, A, some multiple of A, right? Now, we don't know what T is, and that's because we're hoping to capture sort of every point on the line. So we want to allow T to vary. But for any given point on the line, we can say that it's B plus TA for some T. And so that's what they're writing here. OP, which they're calling R, this vector here, is this OP0 or B plus TA. And then they say we have established the following proposition. The vector parametric equation, remember we're going to get an equation for every vector here, or we could say every point on the line, which we could also associate with this vector. The vector parametric equation for the line through the point P0, through the point P0, whose position vector, we call it O. P0, the position vector just means the vector associated with that point. We also call it B, and B is going to have some coordinates. In this case, it's going to be P0 is going to have some coordinates, B1, B2, B3, and so B is going to be B1I plus B2J plus B3K. We can express it this way, or we can express it this way. And A has some coordinates also, which we can express either as A1, A2, A3, or we're allowed to express it this way. And the vector equation is B plus TA gives us R. Okay, so we accomplished our goal of writing a vector equation for a line. So we're given a vector A, and we're given a point B, or a point P0 associated in the vector associated with what we call B. Then we can write this equation for our line. So this is a different way of writing the equation of a line, but actually, if you think about it, you probably haven't seen the equation of a line in 3 space, but here we've accomplished it in 3 space. Now we have, of course, seen equations of lines in 2 space, and they usually involve x and y, and this works just as well in 2 space, but this also works in 3 space. We don't really have a great way of doing this in 3 space. with x, y, and z. But this provides the equation in 3 space, and in fact, in any space. It could be 4 space, or 5 space, or R6, or R7, or whatever. Okay, now note that we call this a vector equation. So that means that we should have a vector on the left side and a vector on the right side. That is, on the right side, this should be a vector somehow, and this should also be a vector. Now remember what we said when we say that 2 vectors are equal. So on the left side we have a vector, on the right side we have a vector. We're saying that they're equal. Remember what that means. This was at the very beginning of our discussion of vectors. We had to say what we meant by the fact that 2 vectors are equal. For example, if you have a vector A, looks like this, and a vector B, which looks like this in R2, when do we say that they're equal? We said that the order is important, and it literally means that this component of vector A has to equal this component of vector B, and this component of vector A has to equal this component of vector B. So in other words, A1 has to equal B1, and A2 has to equal B2. So really, when we say that these 2 vectors, A and B, are equal, we're really getting actually 2 equations. We're getting an equation that A1 equals B1, and we're getting another equation that A2 equals B2. So if these were in R3, then we would actually generate 3 equations from saying that A is equal to B. We'd say that this has to equal this, and A2 has to equal B2, and there'd be an A3 has to equal B3. So we generate a bunch of equations from a vector equation. So if we have a vector equation here, and if, I think we're talking about R3 here, so this really has to be, it has to generate 3 equations, because the left side should just evaluate to some vector, and the right side should evaluate to some vector. So we have one vector equals another, and this is an R3, so that should give us 3 different equations. So let's think about what they are. So remember, this is R here, which we can also call OP. So we have that. So we'll say R, which is also called OP, is equal to this plus this. But B, B is here, and it's associated with the point P sub 0, and but it has some coordinates, which we are calling B1, B2, B3, but we said we can switch back and forth between thinking of them as coordinates and thinking of this as B1i plus B2j plus B3k. So let's write that. So we have B1i plus B2j plus B3k for this part here. And then we have T times A, and A also is here. It's a vector, so we can think of it as having coordinates, or we can think of it in terms of ijk and multiplying the associated coordinates with ij and k, and that's what they're going to do here. So we're going to have T times A1i, A2j, and A3k. So we can do that. We're just right like this. Now we can collect terms, and we can figure out what's multiplying I. So B1 and TA1. So we can write that as something times I. A1T, that's this part here, A1T, plus B1 times I. And then we can figure out what's multiplying J, and that's A2T, A2T plus B2, and so on. We can do the same thing with K. Okay, so we just did a little kind of algebra here, but we haven't generated those 3 equations yet, the associated 3 equations. Okay, so next we're going to take OP, which is this here. So P is just some point on the line. So it's not fixed. It could be, we want to allow it to be anywhere, but we still can give it coordinates. and we'll just give it the coordinates x, y, and z to kind of make it arbitrary. We don't want to say x1 or something like that because that implies that it's fixed. We don't want to think of it as fixed. We want to allow it to be any point on the line. So we're just going to call it x, y, z. So OP has the point P has coordinates x, y, z. So we can say the vector OP, we could say is x, y, and z, but we can also, again, we're supposed to be able to do this in our heads, see that we can also write it as xi plus yj plus zk. So now we just finished this and this, and now we can rewrite OP like this. So now we have this, maybe I can write it. We can take this, which is OP, copy it, and paste it here, because it's OP. So now we have this equation here, which now we can say that they have to be, the things that multiply I have to be equal. So what multiplies I here, x, and what multiplies I here, this thing, so they have to be equal. The things that multiply j have to be equal, so y has to be equal to this, and z has to be equal to this. And so we get the three generated equations. We're saying that the x coordinates have to be equal, the y coordinates have to be equal, and the z coordinates have to be equal.